Hello everyone. So in this video, we will talk about the basics of the simple linear regression. So in fact, up to now, what we see is, well, we say that there is a relationship between x and y, right? You have dots like this. So how to find the line which passes through these dots? Remember, in the previous video, we said that, well, the data that you have over the line are called y hats, yi hats, and the real data that you have, for example, this one is yi. So what you do is you just take the deviation, the error between the estimator and the real value, which is yi minus yi hat, right? And then square this error and sum them up. So this is what we call an SSC, sum of squared errors. And if you just minimize this, find the B0 and B1 so that minimizes yi minus y hat, which is in fact B0 plus B1x I, let's say, squared. Then this is the best line that passes through this point. Okay, so up to now we didn't say anything about linear regressions, random variables, and so on and so forth. But in the previous slide, what we did was we just found a line that passes through the points. So this line just shows that there is a relationship between x and y values. So there's a trend that goes up, and there's a scatter around this line. Okay, now assume that the weights of people in this university, so let's say this random variable y, so this is a random variable y, and it has a following distribution. Okay, so y is normally distributed with mean 65 kilograms and with standard deviation 60 kilograms. Okay, so it has a distribution like this, right? This is normal, right? And in the middle, you have little in the middle, you have 65 kilograms, and the standard deviation is 10 kilograms. That's great. And this is my view. Okay, so this is the distribution of this random variable, the weight of people in this universe. Okay, so what does this mean? So for example, if you just take, I don't know, 3 many guys from this distribution, it can be, I don't know, 68 kilograms or 60 kilograms or 71 kilograms or I don't know, 63 kilograms and so on and so forth. Okay, so these all can be selected from this distribution, right? Okay. So, well, if we know that for any constant a and a random variable x, we can write this, right? So expected value of a constant, okay, let me just show over this. A constant plus the random variable x, that's equal to a plus expected value of x, right? So for example, if you just look at the random variable above, you can just say expected value of 5 plus y, that's equal to 5 plus expected value of y, which is equal to 5 plus 65, and that's equal to 70 kilograms, right? And moreover, the variance of, for example, 5 plus y is equal to just variance of y, okay? Because, well, this is a constant, and remember the formula for this one is equal to so if you have something like this, if you have something like ax, right, plus by, if a and b are constants, scalars, and x and y are random variables, then the variance of ax and plus by is equal to a squared times variance of x, okay, plus b squared times variance of y. Right? Since variance of 5 is equal to 0, so there is no variance associated with this because it's a constant. Right? That's a constant term. Then, so this is 0, hence the value of this variance 5 plus 5 is equal to variance 4. Okay. Now, so I have this random variable here. Okay, the y is the random variable of the students in this university. Okay, then I can write it as So this is not W, but this, let's say this is Y. Okay. Okay. I just corrected that one. So Y can be written as 65 plus epsilon, where epsilon is a normal random variable with 0 mean but 10 standard deviation. Okay? So what I write is, so Y is equal to 65, which is in fact the mu, plus epsilon. Okay? So Y is a random variable. Epsilon is a random variable. Okay, and 65 is a constant. So what I do is I just write the random variable, the normal random variable y, okay, which is normal with 65 and standard deviation of 10. I write y as summation of a constant, which is its mean, right? Plus another random variable, epsilon, which is also normally distributed. But now it's normally distributed with 0 mean because, but I wrote the mean just here, okay? And standard deviation that's equal to 10, okay? So that's great. I'm able to separate the random variable, the normal random variable, into two parts. The first part just stands for the expected value mu, and the second part just stands for the standard deviation or the variation. Okay, so I'm able to separate the random variable into two parts. Again, so y is equal to its mean, which is 65 in our example. Okay, so this is equal to 65 in our example, plus epsilon, which is normally distributed with mean 0 and with standard deviation, with the same standard deviation, okay? With the same standard deviation as well. So again, I just divide y into two parts, a constant, which is the mean, and the random variable, a normal random variable, which is epsilon with the same sigma, okay? Now, let's go further. And let's say y sub x, okay? Y sub x denote the random variable of weights of people who are x centimeter tall, okay? For example, y 180 denote the random variable of weights of the people who are 180 centimeters, okay? So let's think of this like this. So let's say this is, the distribution of y. So this is the distribution of y 180, right? So this is a random variable with some mean here, okay? With some mean here and with a standard deviation. Okay, let's say, so it's normally distributed with some mean. Let me just write it like this. I don't know how I just represent it. And standard deviation of 180 there, okay? So this is the distribution of people who is 180 centimeters tall. Right? So, similarly, let me just write the random variables associated with these heights. Okay, so let's say y sub 160 be the random variable that denotes the weight of people who are 160 centimeters, right? So let's say this is normally distributed with 63.6 kilos and with 10 kilograms standard deviation. Similarly, let's say 170, this is the random variable for weight of people who are 170 centimeters tall, and it's normally distributed with this mean and with the same standard deviation. So as you see, the standard deviations are same. They are just scattered around the mean with the same standard deviation, with the same scatter scale. Okay, and but their mean just differ. Okay, so this is what we expect, right? So as the height of people gets taller, they just get heavy, right? So again, the random variable. This is the random variable shows the height of people. Uh, shows the weight of people who's 170 centimeters tall, and this, let's say this is 190, which shows the distribution of weight of people, kilogram of people who's 190 centimeters tall. Okay, so let me just, okay, let's do it like this. So I will do something like this, right? So let me just, so here, let's put it like this. So I have here 63.6. Okay, so this is the this is the distribution of people who are 160 centimeters tall. Okay, so its mean is 63.6, right? Its standard deviation is 10. So far, so good. Okay. So let me change the color. Let me just make it green. So I have, let's say, let's here I say this is 72.2, okay, and this is the distribution of people who are 170 centimeters tall, okay, and let me just again change the color, and well, let me just write, okay, so this is 80.8, and this is the distribution of weight of people or students whose height is 180 centimeters tall, right? And finally, let me just change the color to, I don't know what else, let's do black. I have 89.4, and this is the distribution of people whose height is 180 centimeters. As you see, well, these are the, so you have four different distributions for four different group of people whose height are different than each other, okay? But the thing is that, well, their sigmas are same, okay? As you see, so the dispersion around the mean is the same for all of them. But the only change is that, well, their mean is different than each other, okay? So how can I write this random variable? Recall, this is the random variable, okay, with distribution 63.6 and its standard deviation 10. I can write it as mu sub 160. What does this mean? This is the mu of this distribution, which is 63.6, right? Plus epsilon. And again, what is epsilon? Epsilon is a random variable, normal random variable with zero mean, so its mean is zero, and its standard deviation is 10. So I am able to write all of the random variables as a sum of constants, which is mu, okay, mu of this, the distribution of this random variable, okay, plus epsilon, which is a normal random variable with zero mean, but with the same standard deviation as y sub 170, okay, so which is equal to, in fact, 7. So epsilons here have the same standard deviation, which is equal to 10. Okay. So this is how can I write the random variables associated with different means with different heights. Okay. Okay. So we just separated the, as I said, the deterministic part, which is the mu of x, and the random part, which is epsilon, right? So as we said, in general, there is a relation between the height and the weight. So the taller you are, the heavier you are. Right? Well, it turns out that, well, we cannot affect the random part. Okay, so the epsilon, well, that's a random variable. Its mean is zero. It has a standard deviation, it scatters around the mean. So you cannot directly relate that random variable with something else. Okay, but what we can do is we can just relate the the height and the weight. We can relate the height and the weight through what? Through the deterministic part of the weight, which is mu. Okay. Well, let's assume this relationship is linear. Okay. So in general, if there is a relationship between any two variables, okay, x and mu, you can just write it like this. So let's assume mu is equal to some constant plus a slope or a coefficient times x. Okay. So if there are two variables, then you can write the relations, the linear relationship between them using by defining two parameters. The two coefficients, beta 0 and beta 1 here. So this is, in fact, this is a definition of a line, remember. So this is x and this is mu. So this line just starts when x is equal to 0, you have beta 0 here. Okay, so this is beta 0. It just goes up, and remember this alpha, the tangent alpha, the slope is equal to what? The slope is equal to beta 1, right? Okay, great. So for our case, how can I write this? Since we said that, well, the relationship should be between the deterministic part of the demands and the variable, the height, okay? We can write it like this. So remember, we said that, well, mu sub 180, or we said mu sub 170, okay? So in fact, this was something like mu sub x, but instead, let's use this mu sub y given x, or mu sub y. So what does this mean? This says that, well, this is the expected value, okay, the expected value of the random variable y, okay? So remember, we were talking about the random variable y, which is the weight, okay, the kilogram. So this is the expected value of the random variable y. Or we can just use it as the expected value of the random variable y given x. What does this mean? It means that, well, this variable y depends on x, and once you give x, the mean of y changes. In fact, this is what we have, right? So if x is equal to 160, you have a different random variable, hence you have a different mean. If x is equal to, for example, 190, then you have a difference mean and you have a different random variable. We can use both. We will use both mu sub y given x or mu sub y. So this is how we can construct a linear relationship between the expected value, okay, the constant part of the weight and the height, okay? So in our example, remember we have 4 points. If you just check, you can see that we can just write mu of y, okay, the expected value of y is equal to minus 74 plus 0.86 times x. So what does this mean? So for example, if we just write 160 here and multiply it with 0.86, and if you just subtract minus 74, you will see that you will get the mean of 160, right? So let me just go back. So what is 160 here? Okay, so this is what we have, 63.6, right? Or if you just write 170 in that relationship, then you will get 72.2, okay? So so if you just write x is equal to 160, you will get mu of y equal to 63.6. If you just write 170, then this will be your mu of y. Okay. So you can write this relationship between these two variables, the expected value of mean and the height, expected value of the, weight, kilogram, between the height can be given by using this formula. Okay. So just look at this. So this is mu of y. Let me just change this. So mu of y is equal to minus 74 plus 0.80. Let me check. 86 times x, which is the height, right? So for example, if you just put 150 here, then you will get 55, right? Or if you just put 170 here, okay, into the formulation, then you will get 72.2, right? And this is the, so this is the line that you have. So the formula of this line is equal to mu of y equal to minus 74 plus 0.86 times x, okay? So you may ask, so the intercept is -74, so why we have 55 here? Note that this intercept can be observed whenever you have x is equal to 0. So here x is equal to 150, right? So this x is x. This x is mu of y, right? So this is, again, this is not y itself. This is not a random variable itself, but this is the mu of y. Okay? So when 150, you have 55. When 155, so you have almost 60, which is 59 points. So this is 59 point. So this is 59.3. If you have 106, which is here, this is 100. This is 63.6, right? So let me just this. This is 63.6. If this is 155, then you have almost what? 59.3, and so on and so forth. Right? Okay. So again, note that this is for, sorry, this is for the mean of the weight. Okay. So this is the relation between the mean of the weight and height. So for the random variable, we have this equation, remember. So the random variable is equal to the mean, which is also mu of y, plus epsilon. And what is mu of y? Mu of y is equal to beta 0 plus beta 1 times x, right? So in fact, we have this. The random variable is equal to the constant term here, beta 0 plus beta 1 times x, plus the random term epsilon. And this random term, remember, this is normally distributed with zero mean and standard deviation, which is equal to the standard deviation of the original random variable y. So for example, just look at this one, right? And of just a minute. So in the light of this, just look at this this plot. Okay. So here, let me just change my color. So here, again, what we say is, so for example, when we have 165, this is, right, this point is 165, you have 67.9. Okay, so this is what this is, mu of y. Mu of y at what? Mu of y at 165, at when the height is 165 centimeters. Okay, so the mean of the random variable y when height is 165 centimeters is equal to what? 67.9 centimeters. So what is the standard deviation? The standard deviation is equal to 10 centimeters, right? So, well, there's a distribution, right? Or there's a distribution. So the distribution is normal distribution. Right? So so you can just plot it like this. So this is, let me say, so let's think of this as a three-dimensional plot. Okay. So you have something like this, right? So this is just like this. Right? So if you just look at this axis, so this is, or let's say at this axis. So this is the mean of the distribution, and you have a random variable here. Okay, so this random variable is y, okay, at where whenever x is equal to, let's say, 165 centimeters. Or here, okay, here you have 180, which is 80.8 centimeters. Okay, so the mean of random variable y at x is equal to 180 centimeters is mu of, let's say, y is equal to, let's say, mu of y at x is equal to 180 centimeters is equal to, let's erase this part, is equal to what? 8.8 centimeters, right? And sigma is equal to, again, 10 centimeters. So again, I have a distribution like this. Okay, so it just goes like this. It comes down like this, right? And this is the This is the axis, right? This is the axis. So this is where, this is the random variable y, okay, where x is equal to 180. So in fact, this line just goes through the means, okay? So at each point, in fact, you have a random variable like this, right? So so this plot is something like that. So this plot is the same thing, okay? So as you just look at this is x1, you have x2 here, x3, right? x4, x5, and x6, okay? So at each x, you have a mean. So this is the first mean, this is the second mean, third mean, fourth mean, fifth mean, the sixth mean, okay? And at each x1, there is the mean and there is this distribution. So each distribution, you have the same sigma, right? The same sigma. So at each x, we have a different normal random variable with the same sigma. And the line just passes through this x. Okay? So for example, this black dot, let me just change my color. This black dot here, and this black dot here, this black dot here, they are all a realization from this one. Well, so what does it mean? So for example, if this x1 is equal to, let's say, 160, if this is 165, so this single black dot is a guy whose height is 160 centimeters and whose weight is something here, okay? I don't know, but let's say 58 kilograms. And this guy, so this is a specific guy, okay? We just pick this guy from the class, and his height is 165 centimeters, and his weight is something like, I don't know, 68 kilograms, okay? So each black dots here are the realizations of each different random variables, right? And how can we write the random variables in terms of our um, equation? We can say that y1 is equal to, so this is what? This is the weight, this is the kilogram of the first guy, okay, which is here. This is y1. So y1 is equal to beta 0 plus beta 1 x1. Okay, so what is x1? In our example, x1 is 160 centimeters. Beta 0 plus beta 1 x1 plus its error term. Okay, so y2 can be written as beta 0 plus beta 1 x2 plus its error term. Okay, or y6 can be written as beta 0 plus beta 1 x6 plus its error term. So in our case, x2 was 165, okay? So what we do is, at each case, we first find the mean, okay, the mean, which is the constant, and then we just add the random term to there, okay? Okay, so far, so good. So this line, mu y, which is equal to the expected value of y, and which is equal to beta 0 plus beta 1x, this line is called the population regression line. And it just summarizes the trend in the population between the predictor x and the mean of the responses mu y. Okay? So again, x is sorry, x is the independent variable. Sorry for this. So here, the variable x is the independent variable. Okay. So again, we say that, well, this regression line is called the this equation is called the population regression. So it just summarizes the trend in the population between the predictor x, okay, or the independent variable x, and the mean of the responses mu y. Okay. So again, x is the independent variable or the regressors. Well, what you do is you just control them and find the corresponding y. And y is the dependent variable or the mean response. Okay. Okay, they are uncontrolled and they just depend on the values of x. Okay, so here beta 0 is the intercept and beta 1 is the slope. Okay, I just remove the names. So it's better just to call the x variable as the independent variable and y as the dependent variable. So in our example, x is the height, right? And y is the weight. So the weight depends on the height. So that's why we call y as the dependent variable. And here beta 0 is the intercept and beta 1 is the slope of this line. Okay, so the problem is, well, we don't know the real betas. Okay, so the problem is we don't know the real betas. And in the next video, we will talk about how to find or estimate these real betas.